The population proportion. Well, in stats, we usually want to study a collection of items. We want to gather data. That collection is known as the population. It would be useful to have information about every piece of data. So information about every individual item in the population. If you gather every piece of information, that's what we call a census. Okay, so an example. There's 1 million people in the city. And what we're interested to know is the proportion of people that would choose a prime number if they were asked to pick a number between 1 and 100. The probability that they choose a prime number, well, that's what we call the population proportion. There are 25 prime numbers that are less than 100. So the probability of them picking one would be 0.25. When we went and actually surveyed our population, I did a simulation, of course. I didn't actually go out and talk to 1 million people, but ended up creating 249,925 of them chose a prime number. You can't predict the response. That's the point. So the result of the census is not necessarily going to agree with the population proportion. The population proportion, I guess, is what we expect to happen. So what's a sample proportion then? Conducting a census is often unrealistic. It's going to take too long. I mean, if you're talking about a population of a city, that's 1 million people you're going to go and talk to. Population of the whole country, you're talking about multiple millions of people. Cost. Well, if you're going to do such a big census, you're going to employ people to go and do that. And so that can be a costly operation. Analysing the results. You're going to gather a lot of information. So to go and analyse all that data is going to be time consuming. So therefore, a more realistic aim is going to be to take a subset of our population, a sample of the population. And when we do that, that is called a survey. So a survey is just when we gather information from a sample. A census is when we gather information from the whole population. Now, ideally, we would like our sample to have all the same characteristics of the whole population. For example, if 45% of our population was male, then we'd like 45% of our sample to be male. So I went and surveyed 100 people now from the city because 1 million turned out to be time consuming. We asked them to choose a number between 1 and 100. And in my survey, 29 of them picked a prime number. So the sample proportion would be 29 over 100. And you'll notice the notation for sample proportion. We put a caret over the p. So 29 over 100, 0.29. And that is different from our census. But again, it's unlikely that it will be the same. If we're dealing with a binomial distribution, so our sample proportion will be x over n. So the probability that our sample proportion ends up being x over n will be the same as the proportion of x equals x. That's our binomial probability. So we get NCX, chance of it happening to the power of x, chance of it not happening, n minus x. The expected value, that's what I was saying before, the expected value always turns out to be the actual probability. We are expecting the sample would have the same probability as the population. The variance, though, will change. The variance is going to be still p times 1 minus p, but now we will divide it by the number of people in our sample. So p hat will give us an estimate of our probability. We're expecting it to be the same as the population. Probably won't be, but that's what we're expecting to happen. Here's this example then. So prior to our survey of 100 people, we wanted to see if that would be a big enough sample to go and draw conclusions about our population. So we ended up running 50 simulations using a spreadsheet. Now, p hat is going to represent the proportion of people choosing a prime number. And in our 50 simulations, that's what we ended up with for p hat. So as you can see, sometimes it did turn out to be what we were expecting. Most of the time it did not. Remember, we were expecting 0.25 because there are 25 prime numbers that are less than 100. The variance of our sample, 0.25 times 0.75 divided by the number of people, 50. So we should see in our data there, in those 50 simulations, that the variance between the different ones, 0.00375. So let's say I'm going to be happy if our survey produced an estimate that's within 5% of the actual value. So probability 0.25. I want p hat, our estimate, to be within 5% of the actual value. So it'll be between 0.2375 and 0.2625. P hat is going to be x divided by n. N is the number in our sample. So x is going to be in between 23.75 and 26.25. So in our 100, I want to see if we get in between 23.75 prime numbers and 26.25 prime numbers. Now, of course, they're not going to pick 23.75 or 26.25. So I'm going to push the boundaries out to those limits. So it's like I'm going to find the ceiling of the upper limit, which is 27, but I'll find the floor of the lower limit, which is 23. Okay, but remember it's binomially distributed. We've got 100 numbers, and the probability we're working with is 0.25. So using binomial probability, I end up with 0.43601. So there's a 44% chance that our survey is going to produce an estimate that's within 5% of the actual results. What if I chose to do a normal approximation? Because remember, sometimes those binomial ones, too many calculations to do. So if I use a normal approximation, so p is 0.25. Remember, p hat we're saying is going to be in between 0.2375, 0.2625. Let's find the standard deviation, because I'm going to need that to work out our Z-score, 0.0612. So using that information, we can now standardize our data. So Z, well, 0.2625, that'll become 0.2625 minus the mean, 0.25, divided by the deviation, 0.0612, and that's going to be 0.2042. And, well, because it's the absolute value of Z, because we're symmetric either side of the mean here, we get twice that value minus 1, which works out to be 0.1618. So there's about a 16% chance that our survey will produce an estimate. Well, 16%, that's even worse than the last one. So from that, we can only conclude that a sample size of 100, that's not going to be good enough to model the entire population. We're going to need a lot more people surveyed. We're going to be okay with that. The example I did there was showing you why we find samples. Let's look at a more realistic example of what we're going to expect to see. A recent census shows that 20% of adults in the city eat out regularly. Now, a survey of 100 adults in the city is conducted to find the proportion who eat out regularly. They're helping us out here by telling us what the answers should be. So the mean and standard deviation, 0.2 and 0.04. Okay. Well, the mean, notice I put X bar because we're dealing with a sample there. Mu we tend to use for the mean of a population, whereas X bar we use for mean of a sample. So X bar is equal to P, and that is 0.2. 20% of the adults eat out regularly, so that is what I am expecting. That's why I think it was important here to write that X bar is equal to P, because if I just wrote down 0.2, well, that's the answer they gave me. So I've got to see that I know how I got that answer. So by simply saying, well, it's equal to P, the probability of the population. So if I show that it's equal to P, remember P was the population proportion All right, let's find our deviation. Again, here you'll notice different notation. Sigma is the notation for a population. S is the notation for a sample. So S is equal to the square root of P1 minus P, but we divide by the size of the sample. So 0.2 times 0.8 divided by 100, and sure enough we get 0.04. Okay, part B, they've given us a piece of the table, and they now want us to standardize the normal distribution to go and estimate the probability that at most 15 of those that we surveyed eat out regularly. So standardizing our data, well, Z is going to be less than 0.15, at most 15. So less than 15. But 0.15 minus 0.2 over 0.04. And that works out to be minus 1.25. Now, the table they've given me doesn't have minus 1.25, but remember we can use 1 minus the 1.25. And looking up our table, 1.2, there it is. Read across to when it's underneath the 0.05, we get an answer of 0.8944. Subtract that from 1, and we get 0.1056. Here's another example. An online retailer claims that 90% of all their orders are shipped within 12 hours of being received. Now, on a particular day, 121 orders were received, and 102 orders were shipped within 12 hours. So what is the sample proportion of orders shipped within 12 hours? Well, my sample is the particular day, and there were 121 orders. So 102 divided by the size of the sample, and that gives me 0.84. The distribution of the sample proportion, we're told, is a normal distribution. Assuming the online retailer's claim is true, what's the probability that in a random sample of 121, so not necessarily our sample, but in any random sample of 121, less than 85% of all orders are shipped within 12 hours? So our expected value would be 0.9. They told us 90%. The variance on that one, 0.9 times 0.1 divided by the size of our sample, 121. And it's quite a small number there. I put it in scientific notation. 7.438 times 10 to the negative 4. So our sample is normally distributed, average of 0.9, variance of 7.438 times 10 to the negative 4. We want to know the probability when that is less than 0.85. Let's standardize the normal distribution. So we'll turn it into a Z-score. So when is Z less than 0.85 minus the average, 0.9, divided by the deviation, which is the square root of the variance. So we're looking for when Z is less than minus 1.83. Now, again, our table doesn't have negatives, so we want 1 minus 1.83, and that turns out to be 0.0336. Well, using that result, evaluate the reasonableness of the online retailer's claim. And again, this is going to be a bit subjective, but part 2 is telling me there's a 3.4% chance of shipping less than 85% of orders within 12 hours. In part 1, our sample proportion was 84%. Now, that would have only occurred by chance 3.4% of the time. So, therefore, most of the time it's not happening by chance. Now, our retailer claimed that 90% of the time they'll be able to do this. Yet, our sampling is telling us, no, that's not going to happen. So, our retailer's claim is a bit dubious. All right, well, 17D, have a go at some sampling and see how we go there.